Welcome to the webinar Traffic Visibility for IP Networks: Challenges of New Encryption Protocols. In this bite-sized webinar, we will explore the impact of encryption and new encryption protocols on IP networks. We will then look at the tools and technologies used for encrypted traffic visibility. I'm Ariana Lin, Principal Analyst and Senior Editor at the Fast Mode. And with me today, I have Tobias Roeder. Tobias has more than 8 years of experience in product development and currently works as an application engineer for the Deep Packet Inspection software RNS Space 2 at IPOC, a subsidiary of the Rohde & Schwarz company. We will be starting with the Fast Mode session discussing encryption and the visibility challenges faced by networks as encryption protocols are introduced. We will also be looking at the technologies currently used to circumvent this visibility loss, focusing on deep packet inspection. This will be followed by a solution presentation by Tobias, who will be discussing advanced DPI techniques such as machine learning and deep learning, and how these address the visibility challenges from encryption. If you have any questions during any of the sessions, please input them into the chat box on the right side of the screen. We will reach out to you via email with the answers and feedback. We'll also get in touch with everyone who signed up with a full recording of this webinar. Okay, so let's begin. First, we are going to quickly go over some of the basics of encryption and some recent trends. Encryption is essentially the process of transforming information into an unreadable format, known as ciphertext, to protect its confidentiality and integrity from unauthorized access or interception. Encryption begins with a handshake initiated by the client to the server. As part of the handshake, the client informs the server about the cipher suites it can use. After negotiating and reaching a mutual agreement on a cipher suite, the client shares a key with the server. Subsequently, the client encrypts the plaintext message using the agreed upon cipher suite and sends it to the server. On the server side, the message is decrypted using the key provided by the client. As mentioned earlier, encryption ensures confidentiality, integrity, and authentication, making the communication between two endpoints secure. Okay, so we often see Transport Layer Security (TLS) and Secure Sockets Layer (SSL) interchangeably used. TLS and SSL are cryptographic protocols that provide secure communication over a network. TLS evolved from SSL, building upon its foundation to enhance security and reliability. However, SSL was discontinued in 2018 due to numerous identified security vulnerabilities. TLS has since been widely adopted and is the recommended protocol for secure communication. Well, what about the difference between TLS 1.2 and 1.3? Currently, these are the only two versions of TLS that are widely used. TLS 1.3 was introduced in 2018 and brought significant improvements over its predecessor. One notable enhancement is the reduction in the number of round trips required during the handshake process, resulting in a faster establishment of a secure connection. Additionally, TLS 1.3 introduced the option for zero RTT, zero round trip time, allowing clients to send encrypted data in the first round trip itself, further improving performance. Another important change in TLS 1.3 was the removal of RSA and other static key exchange methods which did not support perfect forward secrecy. Furthermore, TLS 1.3 removed weak cipher suites, enhancing the overall security of the protocol. In terms of structure, TLS comprises a handshake protocol and a record protocol. These advancements in TLS 1.3 make it the increasingly popular choice for application developers and end users. Okay, so the prevalence of encrypted traffic has witnessed a significant increase in recent years. As you can see on this slide, according to Google's transparency report, the adoption of HTTPS, which is HTTP over TLS, has surged across different platforms. On a Chrome operating system, the percentage of pages loaded over HTTPS has risen from 47% in May 2015 to a remarkable 99% in May 2023. Similarly, on Mac systems, it rose 44% to 97% during the same period, and on Windows, it rose 39% to 93%. Next, we are going to talk about the impact of encryption on network visibility and explore the developments in encryption protocols that further contribute to this loss of visibility. Encryption presents several challenges that need to be addressed, with one of the most significant challenges being the loss of network visibility. This poses a major concern for networking vendors, as highlighted by a recent survey conducted by IPOC and the Fastmode. The survey, which took place from October to December last year, was participated by 34 top-tier networking vendors and found 85.3% of the participants to consider the loss of traffic visibility as a major challenge. But how exactly does encryption impact network visibility? Let's take a look. For this diagram, we are assuming an HTTPS TCP/IP model. We can see here that the IP packet comprises of packet and segment headers and the packet payload. The payload contains an HTTP header and the actual application data being transferred. Traditional network observability or monitoring tools rely on the packet payload for traffic analysis. When network traffic is encrypted with TLS 1.3, this packet payload is transformed into an unreadable format through encryption algorithms. In the diagram, as the encrypted IP packet passes through the network, it maintains its integrity and confidentiality. However, this encryption also limits the ability of network monitoring systems to analyze the payload for security threats or to identify specific applications or protocols. The encrypted payload acts as a secure tunnel, shielding the actual data from unauthorized access or tampering, but at the same time impeding the visibility needed by network administrators. Some protocols such as IPsec and QUIC encrypt the segment and packet headers as well, but we will go into that in detail later. When the payload is encrypted, network administrators lose access to several types of crucial information. On this slide, we can see 5 types of information that are hidden as a result of encryption. Firstly, they lose visibility into malware and threat information that could help identify and mitigate security risks. Secondly, they lose the ability to scan the packet payload for specific information. As an example, an enterprise may need to inspect traffic payloads to see if sensitive information is leaving the enterprise network, potentially hindering efforts to protect confidential data. Compliance with data privacy and security regulations such as HIPAA also becomes harder to ascertain due to the lack of access to packet payload information. Furthermore, encrypted traffic makes it difficult to identify the applications in use, for example Facebook, WhatsApp, or Office Online. Lastly, it also obscures the services being used. For example, given it's a Facebook app, it's difficult to tell if it's a video or a text message. Out of the 5 information layers, our survey reveals that the loss of information on malware and threats is encryption's biggest visibility downside. Nearly 60% of the vendors see significant impact in this area. Loss of packet payload information comes second, with 47.1% of the vendors stating the same. As mentioned earlier, the diagrams used before are specific to an HTTP plus TLS 1.3 TCP/IP model. While TLS 1.3 is already a complex protocol, we expect to see the growth and adoption of stricter encryption protocols that conceal more data. In order of popularity, TLS 1.3 0RTT is gaining increasing adoption with support from major browsers and servers. TLS 1.3 0RTT is a mode for TLS 1.3 session resumption and reduces round-trip time by up to 2 rounds, effectively removing much of the data available in the handshake process. Handshake information is also reduced in the case of ESNI, encrypted server name indication, and ECH, encrypted client hello. As their name suggests, ESNI and ECH encrypt the server name indication, SNI, and the client hello during the handshake process respectively. ESNI is gradually gaining traction, while ECH is currently in the early stages of development and expected to see gradual adoption. On the DNS front, we are seeing growing adoption for DNS over HTTPS, which encapsulates DNS traffic within HTTPS, with growing support from major browsers and DNS providers. DNS over TLS also has a steady adoption rate, while DNS over QUIC currently has limited adoption with ongoing research and development. That brings us to QUIC itself, which stands for Quick UDP Internet Connections. QUIC, unlike TLS, encrypts the transport layer and is experiencing rapid adoption with implementation by major platforms and services. We will go into it in more detail in the next few slides. To demonstrate the difference that encryption protocols have on network visibility, here we can see a TLS 1.3 handshake process. As illustrated, only the final request, which contains the actual application data, is encrypted, if you look at the orange dotted line. This is in contrast to a TLS 1.3 plus SNI handshake, where the SNI component of the client hello is encrypted, effectively hiding the intended server hostname. Again referred to the orange dotted lines. ECH builds upon this and goes on to encrypt the entire client hello. More specifically, it encrypts the inner extensions of the client hello, including the SNI and the ALPN, effectively hiding most of the connection details from network administrators. QUIC takes this a step further with its significantly shortened handshake and default built-in encryption. Once a QUIC connection is established, all subsequent data exchanged between the client and the server is encrypted by default, providing secrecy throughout the entire communication. This encryption also extends to QUIC packet headers. Unlike traditional transport protocols like TCP, which rely on additional encryption layers like TLS to establish a secure connection, QUIC combines encryption and transport functionality within a single protocol. This integration allows QUIC to establish a secure connection right from the beginning, without the need for separate encryption layers. In the TCP/IP model, encryption typically operates at the security layer, but in the case of QUIC, the encryption extends into the transport layer itself, providing a higher level of confidentiality throughout the entire communication process. This diagram illustrates how QUIC's encryption encompasses both the security and transport layers, severely limiting the information available to network administrators. Okay, now that we have gone over the impact of current and emerging encryption protocols, we will now explore how the resulting lack of visibility can impact both network functions and network outcomes. A lack of network visibility has significant implications for various categories of network functions. On this slide, we can see 5 major categories. Under each function, we can see some examples of specific network functions. Encryption compromises security measures. Tools such as firewalls or cloud access security brokers, CASBs, can no longer identify anomalies or malicious traffic, as these can be hidden in encrypted packets. This increases the network's susceptibility to attacks. Secondly, it impacts network performance management and service assurance. By not being able to distinguish one application from another, application KPIs such as latency, packet loss, and throughput cannot be ascertained accurately, leaving degradations in service quality unmonitored and unremediated. Thirdly, it creates various blind spots in traffic analysis, with partial information on traffic flows and very little data on encrypted applications. This impacts network planning and development. More importantly, encryption cripples traffic processing. Prioritization of certain applications, diagnosis of traffic bottlenecks, and efficient allocation of resources by traffic type becomes challenging. So does the caching and compression of frequently accessed heavy content. For mobile networks, encryption makes it difficult to implement application-based control rules and privileges. We discussed earlier how malware and threat information is the information layer that is most impacted by encryption. It's not surprising, therefore, that network security, which involves tools like intrusion prevention, SASE, and data loss prevention, is named as the network function that is most impacted by loss of visibility, with 30.8% of vendors seeing significant impact. Network performance or service assurance and analytics come close, with 30% and 25% of vendors respectively stating that these are significantly impacted by encryption-induced visibility loss. Policy control seems to be the least impacted, with nearly a third not seeing any impact from encryption. The impairment of network functions naturally impact network outcomes. When tools such as firewalls, advanced threat protection, and intrusion prevention systems fail to identify and block threats in real time, the network becomes susceptible to threats, abuse, and fraud. 70% of vendors agree that this is the worst outcome from encryption-induced visibility loss. Other long-term implications include high network costs, the inability to execute SLA-based plans, poor traffic performance, and high latencies. Not to forget poor network decisions and the lack of support for critical applications, which require priority lanes or low latency routes. We will now discuss how network visibility can be restored with the help of certain tools and technologies. First, let's look at the demand for encrypted traffic intelligence, referred to as ETI. ETI is the analysis of encrypted traffic, focusing on the identification of protocols, applications, and services, and the behavior, performance, and security attributes. According to our survey, nearly 4/5 of vendors plan to integrate ETI into their networking solutions. There are several tools available for encrypted traffic visibility. The first is the decryption of traffic to enable inspection. Frequently referred to as TLS inspection, this involves intercepting encrypted traffic and decrypting it for analytical purposes. To accomplish this, organizations often deploy a middle box such as an SSL or TLS proxy, which acts as an intermediary between the client and the server. This device has the ability to establish separate encrypted connections with both the client and the server, effectively decrypting the traffic passing through it. The second type of tool is based on behavioral, statistical, and heuristic analysis, which includes metadata analysis and the examination of packet-level data like packet sizes, rates, and interpacket delay. These tools also consider flow data, including the traffic direction initiated by the protocol application and the number of flows, as well as flow entropy and statistical information like mean, median, and variation. And lastly, we have tools leveraging machine learning and deep learning techniques, utilizing algorithms such as k-nearest neighbors, LSTM, decision tree learning, CNN, and RNN. So why can't we just use TLS inspection to inspect encrypted traffic? The answer is, while it delivers the same visibility as if there were no encryption, it comes with way too many limitations, including, ironically, things like security. We asked vendors how they felt about using decryption. 61.8% of participants say that security is a concern when using TLS inspection, as the plaintext data is revealed in the TLS chain, exposing it to malicious actors. 52.9% cite regulatory concerns, as certain types of data such as healthcare, banking, and personally identifiable information cannot legally be inspected. Other concerns include configuration complexities, high resource utilization, high latencies, incompatibility with new protocols, limited functionalities, and incompatibility with certain applications. Okay, so onto the last segment, we will now quickly look at the deep packet inspection market and the demand for deep packet inspection with encrypted traffic intelligence. Deep packet inspection, known as DPI, combines shallow packet inspection, which focuses on packet headers to identify protocols and basic information, with the inspection of packet payloads for matching patterns using signature libraries. DPI solutions can be classified into different types, including turnkey DPI, which is a complete and readily deployable solution, in-house DPI, developed internally to suit specific vendor needs, open source DPI, publicly available source code for modification and collaborative maintenance, and commercial DPI, which are licensed DPI solutions from third-party providers tailored to specific use cases. According to our survey, 55.9% of vendors state that they are currently using DPI, and over half of those currently not using DPI plan to use DPI in the future. As for the type of DPI, among vendors currently using DPI, in-house and commercial DPI solutions appear to be the most popular options, while for those planning to use DPI, the majority prefer to use a turnkey solution followed by commercial solutions. The emergence of newer and tougher encryption protocols described earlier has challenged traditional DPI, which relies on methods such as pattern matching. These require visibility into packet payloads. As a bigger portion of traffic becomes encrypted and as the use of obfuscation and anonymization techniques to conceal traffic continues, DPI's relevance in identifying traffic flows is often questioned. Can DPI continue to deliver network intelligence like it used to? The answer, of course, lies in the solution itself. DPI vendors with encrypted traffic intelligence, or ETI as we discussed earlier, can easily circumvent the challenge of encryption, and we are already seeing new breakthroughs in this area. For example, the use of behavioral/statistical and heuristic analysis alongside AI-based techniques such as machine learning and deep learning are pushing DPI's traditional boundaries to tackle encrypted traffic. Demand for DPI solutions with ETI appears to be strong according to our survey. 73.7% of participants with DPI said that they currently have ETI capabilities, while 80% of those with a DPI solution without ETI plan on integrating ETI in the future. Of the vendors planning to use DPI, 87.5% said that they will require it to have ETI capabilities. Moving on, we will now learn about ETI from DPI specialist IPOC, a Roden Schwartz company and leader in the network intelligence space. For this, I'm handing the session over to Tobias, who will introduce IPOC's renowned DPI engine, RNS-Space2, and explore its ETI capabilities. Tobias will also present machine learning basics with a confusion matrix example and will run a live demo of the engine.
Hello and welcome. My name is Tobias Roeder and I will guide you through today's session. So let's get started. So what is DPI about? It's a method to analyze data packets, classify IP traffic and extract additional metadata. We give insights on protocol layers, the over-the-top applications, and derived services. Details about our PACE2 engine are that it's fully written in C language without any dependencies. We are optimized for high throughput performance and a low memory footprint, and we can compile our DPI library on different architectures such as ARM version 7 or 8, PowerPC, Cavium, MIPS, and x86. Furthermore, we support any operating system and deploy the library as a C library in shared object or static format, and you implement against our public headers. We support thousands of applications and protocols, including service types, supporting video, audio, or file transfer, and many more. Additionally to the application detection, we extract additional metadata, such as traffic volume, connection durations, generic flow information, and quality of service or quality of experience indicators, which help you understand your TCP performance. The ETI part supports statistical analysis and a combination of machine and deep learning to classify encrypted and obfuscated traffic. On top of that, we support enhancing the product by adding plugins. One of those is our flow data exporter for IPFix exports, a custom app and service classifier, and net tethering detections, plus DNS cacher for first packet classification. So what is the solution strategy IPOC's ETI can offer to tackle new encryption specifications? IPOC ETI combines a mix of machine learning, deep learning, and traditional caching methods in order to regain visibility. On the machine learning side of things, we apply k-nearest neighbor and decision tree models. On the other hand, deep learning, we combine convolutional neural networks, long short-term memory systems, and recurrent neural networks, RNNs. In combination with a DNS cacher, if available, and a simple IP service cacher, we are able to fully understand even these upcoming specifications and gain highest accuracy and visibility on fully encrypted flows. So let us discuss more details about our machine learning offering. In total, ETI offers over 6,000 features, including statistical, time series, and packet level features. Our machine learning and deep learning algorithms are still optimized for high packet throughput, low latency, and a low memory footprint. So how can you quantify the performance of machine learning results? Therefore, you use a confusion matrix. So what is this matrix about? It helps to evaluate and neutrally assess the quality of a learned classification. The classifier assigns the predicted class against the true data points. The matrix is composed of the error types already mentioned. The columns are the predicted classes for the test set, and the rows are the actual labels of the test set. In total, yielding 4 valid result options, either a true positive or false positive, false negatives or true negatives. So how does this look in an application example? Taking our Google Services classifier, which allows for differentiation of a common SNI towards the actual Google-based services, such as Google Calendar, Drive, Hangouts, Mail, or Maps. As you can see, in the comparison of the predicted labels against true labels, we achieve an average and accuracy over 90%, and we will improve those with our weekly binary releases. Another typical use case is the detection of operating systems, which allows for hotspot detection. A typical telco carrier might be able to understand if a user equipment such as iPhones are opening a hotspot, and if so, how many devices connect. Therefore, we are able to analyze the encrypted traffic flows and categorize those into Android, iOS, Linux, macOS, other or Windows operating systems. As you can see in the dark blue boxes, the accuracy again is higher than 90%, allowing for precise detection of certain hotspot use cases whenever there's a conflicting operating system involved on the same subscriber IP address. Let us now go over to the live demo showing a typical screenshot of an encrypted client hello with an encrypted server name indicator. The Wireshark dissector showing here is still capable of drilling down the extensions. However, unlike TLS 1.2 or the default TLS 1.3, the SNI string, encrypted server name, is now obfuscated. So taking the example of serving to ipoc.com, this indicator is no longer readable. And this will cause in the long run any open source or homegrown inspections to go fully blind. Let us now dive into a live demo using PACE2 with ETI enabled. We are using as a databasis real iPhone traffic generated on an iOS 16.3.1 device. And we are inspecting iTunes and iPhone related traffic flows. If ETI is disabled, we see that SNIs such as iTunes.com just yield to a generic detection. However, these flows may transfer real applications such as Apple Music, Apple Maps, or legit iMessage traffic. So let us now switch over to the Docker-based example. We are using this Docker demo image in order to visualize better our underlying C++ engine results, which usually only come in command line version. Now in the GUI of the Docker image, we see that we loaded the latest PACE2 library in version 23.03.24, including ETI enabled. We loaded the same Apple iMessage trace file we recorded on the iPhone. In the flow table view, we see a simple CDR, connection data record, for each flow, containing a unique flow ID plus layer 4 information and the actual 5 tuple, source, destination IP, source and destination port. We aggregate the packet count per flow and the resulting ETI result in the machine learning column, either resulting into iMessage flows, generic flows for the ecosystem, Apple Music flows, or Apple Maps. Let us now take a look at the analytics chart, presenting all these data tables and pie charts and sunburst charts. The most interesting one is the machine learning ETI result, showing that in the Apple Services case, we had a common SNI, meaning on Wireshark or open source, these flows look absolutely identical. However, ETI was able to yield a fraction of music, iMessage, Apple Maps, and generic flows. Same example for the iTunes SNI. We were able to classify the largest chunk of music traffic, the smaller one of iMessage, Apple Maps, and generic flows. To confirm the traffic origin, let's go over to the GeoIP tab here. We see that in total, these flows aggregate to 3 megabytes and they had a destination into US IP address spaces. Thanks again for joining me for today's discussion of ETI, Encrypted Traffic Intelligence. IPOC addresses the challenge of encryption by enhancing its DPI with advanced machine learning and deep learning technologies, delivering a future-proof solution for enhanced, high-performance and low-latency insights. Have a nice day and see you next time.
Thank you, Tobias, for the brilliant explanation and the demo. That wraps up today's webinar. Thank you everyone for tuning in. Hope you found this session insightful. To learn more, download the report Deep Packet Inspection and Encrypted Traffic Visibility for IP Networks at bit.ly/DPI-ETI report. And please email any questions you might have to Andrea@thefastmode, and we will get back to you as soon as possible. Have a good day and see you again.